who work on steam condensers, who know how they're built and how they work. But for others who may see this film, let's briefly explain condenser construction and operation. Steam condensers convert steam to water by bringing the steam in contact with tubes which are cooled by water flowing through them. There are many uses for condensers. An important example is a ship's main condenser, shown here in simplified form. This condenser recovers turbine exhaust steam as water, now called condensate, for reuse in the boiler. This is important because boiler feed water must be pure, and pure water is scarce at sea. In addition, because the recovered water occupies less space than its equivalent steam, a partial vacuum is created at the turbine's exhaust. This low back pressure adds to power plant efficiency. The elements of condenser construction are a number of tubes, 7 or 8,000 in a large condenser, with ends fitted tightly in tube sheets. There are also several tube support plates, an inlet water chest, and a discharge water chest fit tightly against the tube sheets. A shell around the sides and bottom, and the turbine on top complete an airtight chamber for the tubes. The main condenser is located close to the ship's bottom, well below the waterline. Thus, open connections to the sea flood the water chests and tubes. However, there are 2 gate valves which can shut out the sea. With the gate valves closed, you can drain the condenser and open or remove the water chests for interior inspection and repair. In operation, the forward motion of the ship forces a continuous flow of water up the scoop into the inlet water chest, through the tubes, and out through an overboard discharge to the sea. If the ship is not under sufficient forward speed for scoop operation, cooling water is provided by a pump. An automatic one-way valve closes the scoop. The condenser part, filled with steam and condensate, is called the steam side. The part filled with cooling water is called the circulating water side. Because maintenance of the circulating water side presents the greater problem, we'll discuss this side only. Reduced vacuum can be caused by dirty tubes. Dirt is an insulator which slows the rate of condensation. Reduced vacuum may also be caused by obstructions in the tubes or in the inlet water chest, if the flow of cooling water is materially reduced. Condensate is contaminated when leaks let seawater into the steam side. Such leaks may occur in the tube sheet, as cracks, as broken or corroded studs, or as leaky stay-bolt packings. Seawater leaks may also occur in defective expanded joints between tubes and tube sheets. In these joints, tube ends are expanded to make a tight fit in the tube sheet. If a tube is not expanded enough, or if a tube sheet hole is imperfect or dirty, then seawater leaks past the tube and into the steam side. Defective packed joints are another source of leaks. Leaks may also occur in the tubes. One cause of tube failure is an expanded joint that has been expanded too much. The tube is weakened and likely to split. A split can also be caused by twisting a tube while making the expanded joint. Water turbulence in the inlet ends is another possible cause of tube leaks. Metal is worn away in what is called end erosion. If such conditions persist, tubes will fail near the inlet ends. Obstructions, too, can cause turbulence and erosion. In addition, there is pitting and often failure at the point of obstruction. Galvanic corrosion is another cause of tube failure. Let's explain what this is. When 2 unlike metals are immersed in salt water, and the metals are joined by an electric conductor, a flow of electricity results, and the metal from which current flows into the water is corroded. This condition is duplicated in condensers where various metals are in contact with seawater. To reduce galvanic corrosion of condenser parts, zincs are fastened with metal-to-metal contact inside the water chests. Current then flows from the zincs to the other metals. To a large extent, the zincs are corroded instead of the condenser parts. For the purpose of discussion, we'll divide maintenance into 5 operations: preparing, cleaning, inspecting, and repairing the condenser, and finally, testing the repairs you have made. To prepare the condenser for work to be done, first shut off the gate valves. One in the water scoop, and one in the overboard discharge. Then drain the condenser. Remove inspection plates in both water chests and blow out the condenser with steam or air to remove any explosive gases. Remove both water chests and the condenser is ready for cleaning. Cleaning is necessary simply because a clean condenser is better than a dirty one. Furthermore, we must clean it if we are going to inspect it thoroughly. You never know what you'll find when the water chests are removed, but it's almost a certainty that cleaning will be necessary. Scrub both tube sheets. Tubes may be flushed out with water under 50 pounds per square inch pressure, or with air at 100 pounds. Another method is to use a rubber slug. Put the slug in the tube and hold a water gun tightly against the tube end. Then release a jet of water to force the slug through the tube with a squeegee-like cleaning action. At the other end, a curtain stops flying spray and the slugs. You may have to use a brush to loosen dirt or a probe to dislodge stones or other obstructions. So-called non-corrosive tubes actually do corrode when first exposed to seawater. This initial corrosive action forms a thin layer that protects the rest of the tube from corrosion. The protective layer is an extremely thin film. Don't confuse it with dirt and scale, which must be removed. In the cleaning process, if the protective layer is gouged or scratched, corrosion attacks the exposed metal, causing a weak spot. So be careful. Don't use wire brushes, metal slugs, nor anything that can damage this thin protective lining. You inspect the condenser to see what work has to be done. You look for 2 things: leaks and any conditions that may cause leaks. There are several ways to find leaks. The flooding method is convenient for inspection at sea. After draining the condenser, put compressed air in the steam side. Then open a gate valve just enough to let seawater enter slowly. When the water covers a leak, the compressed air bubbles up in the water chests. You can trace the bubbles either directly to a leak or to a tube which is leaking. Watch for bubbles through openings in both water chests. As the water rises, close the lower openings and continue observation through openings higher up. Next, a method of finding leaks in the tube sheet or in the joints around the tube ends. With the water chests removed, have compressed air applied to the steam side. Then put soapy water on the tube sheet. And while you work, watch for bubbles. Bubbles indicate a leak. In another method, the water pressure method, fill the steam side with water to cover the tubes, and then introduce compressed air to force the water out through any leaks. Water coming through the tube sheet area can be traced directly to a leak, and water dripping from a tube indicates a leak somewhere in that tube. If any condensation forms, blow it dry using an air hose. To discover conditions that may cause a leak, visually inspect all parts that can be seen. Look for broken studs, corroded threads, gouges, cracks, faulty packing, and other conditions that may later cause leaks. Look in the tube ends for signs of erosion. You can look further into the tubes with a borescope. This instrument contains a light and a magnifying optical system. You can see only a small area at a time. But by adjusting the borescope's position, you can examine the tube's interior up to the length of the instrument. Another instrument, the probolog, reveals defects in tubes made of non-magnetic metals. There are 4 units: the probe, which comes in sizes to fit standard tubes, the probe puller, the air valve, and the recorder. To use this equipment, select a probe of the proper size and insert it in the tube. Using the air valve, blow the probe to the opposite end of the tube. While the probe puller withdraws the probe, a pen in the recorder draws a line on a moving strip of paper. Lines similar to this are made by good tubes. Wide swings like these, occurring at regular intervals, are caused by structural features such as tube support plates. Irregularities, like this and this, indicate weaknesses. Such records can be read by trained personnel to obtain information of tube wall conditions. Because condensers have such a large number of tubes, cleaning and inspection must be done according to orderly plan, so no tubes will be missed. When you find a defective tube, mark it with a plug so you can find it later for repair. Inspect the zincs, too. Corrosion forms a crust which stops the zinc's protective action. When you remove the crust, you often find that a new zinc is needed. Repairing is mostly a matter of replacing defective parts, such as broken studs, corroded stud bolts, leaky packings, faulty gaskets, and leaky tubes. We'll devote most of this discussion to repairing leaks in the tubes and in the joints at the tube ends. Tube leaks may be overcome by plugging the tube at both ends. A limited number of tubes may be plugged without impairing condenser efficiency. In a complete overhaul, however, all defective tubes are replaced. The location of bulkheads and machinery usually determines whether you work from the inlet end of the condenser or from the discharge end. Machinery must often be moved out of the way. The first step in removing tubes is determined by the location of the working space and by the tube joint. In most naval vessels, the tube inflow ends are expanded to form a metal-to-metal joint and flared to streamline the flow of water. Obviously, a flared end can be removed in this direction only. In some condensers, outflow ends are packed. In other condensers, the outflow ends are expanded, but they are never flared. Packed tubes should be removed from the inflow end whenever practicable. With expanded outflow ends, it is sometimes possible to remove the entire tube from the inflow end. But in this case, you have two expanded joints to break loose. By cutting the tube here, the job is made easier because you free the joints separately, as you remove the two parts from opposite ends of the condenser. With either packed or expanded outflow joints, when you have to work from the discharge side, you must cut off the flared ends here in order to remove the tubes. This is an air-driven rotary tube cutter. This is the cutting bit. Adjust the tool to cut slightly behind the tube sheet so the sheet will not be damaged. This air hydraulic tube puller requires 100 pounds of air pressure for its operation. Teeth at the end of the puller grip the tube and pull it. The teeth are designed to prevent damage to the tube sheet holes, but be sure to adjust the tool so the teeth grip the tube within the thickness of the tube sheet. To pull the tubes from the outflow end, first remove the packing and then cut the flared inflow end of the tube. Adjust the puller so that its teeth grip the tube here. An alternate method is to insert a drift pin and drift the tube out. This is another type of tube removal tool called a de-expander. It is driven by a rotary impact tool, either electric or pneumatic. We can show the operating principle with this cross-section of the tool. As the tool turns in the tube, cutting edges grip the tube wall and pull it in towards the center to break the expanded joint. When both tube ends are expanded, use right hand and left hand tools together so the tube will be turned in one direction. After several rotations of the tube, remove the de-expanding tools and drift the tube from either end. Before installing a new tube, see that the tube sheet hole is undamaged and clean. Grease and oil prevent metal-to-metal contact and must be removed. For packed joints, scrape all the old packing out of the threads in the stuffing box and blow them clean. When the holes are thoroughly clean, you are ready to install the new tubes. It's not easy to string a new tube through holes that you can't see, but you can do it with the guide rod. Before removing the old tube, insert the guide rod. Remove the tube, leaving the rod as a guide for inserting the new tube through the support plates. A tube guide is another aid for installing new tubes in a condenser. A wire spring holds this tool in the end of the tube. The tapered end centers the tube in the hole. With the new tubes in place, the next step is to finish the ends. Always expand the inflow ends first. Allow 1/16 inch here for flaring. Then expand, flare, and grind flush with the tube sheet. Now let's look at the tools you use to make tube joints. First, the tube expander with electric drive motor. The motor rotates a tapered mandrel, which passes through a cage with 3 rollers in equally spaced slots, and through a stop collar. The basic operating principle is shown in this simple model. When you push the mandrel through the cage in this direction, it acts as a wedge, forcing the rollers apart. At the same time, mandrel rotation causes the rollers to travel around the inner tube surface to make the expanded joint. Stop collars are recessed to receive the tube ends. For the inflow ends, use a collar with a 1/16 inch recess. This automatically sets the tube end outside the tube sheet for flaring. For expanded outflow ends, this distance is not critical. Here, use a recessed stop collar that clears the tube ends. Before using the expander, be sure the working length of the rollers is adjusted to leave just about 1/8 of unexpanded tube inside the tube sheet hole. If the rollers extend beyond the tube sheet like this, the tube will bulge, and somebody will have a hard time if such a tube ever has to be removed. Don't let the tube spin. One way to prevent a spin is to have someone hold the tube at the other end, but make sure the tube is not damaged. The operator no longer depends on sense of touch to tell when a tube is properly expanded. That problem is solved now by electric control equipment. This is one of several approved types. A voltage regulator supplies constant voltage through an electric control to the expander drive motor. The control automatically stops the drive motor when a tube is expanded the right amount. The control is factory calibrated for commonly used tubes. These are listed with code letters on one end of the control cabinet. Note the appropriate code letter for the job, and then set the dial selector with the code letter opposite the index mark. Lock it here. Now, with the roller length adjusted, you are ready for operation. To start the motor, push the toggle switch to on position, but don't touch the micro switch. If you do, the motor won't start. The expander turns left. Let the equipment warm up for about a minute. Slide cage and stop collar forward and insert the cage in the tube. Push on the handle, closing the micro switch. Rotation reverses to the right and expanding is underway. As the tube is expanded, the load on the equipment increases. When the load reaches the predetermined amount, the expander is stopped by the electric control. Now, keeping the micro switch closed, pull back slightly on the drive motor handle. Then release the micro switch to start left rotation and withdraw the expander. To flare the inflow ends, select a belling tool of the proper radius so that the tube will be flared uniformly against the tube sheet. Place the belling tool in the tube so that tool and tube are in line. Then flare the tube with a few light hammer blows. To complete the job, grind or mill the end flush with the tube sheet to make a smooth entrance for the cooling water. When you complete all the inflow ends, then do the outflow ends. If these ends are to be expanded, don't forget to use a recess collar, which clears the tube ends. Outflow ends are not flared and may extend beyond the tube sheet up to about 1/16 inch. If there are a large number of tubes to be expanded at the outflow end, do small groups spaced to equalize the strains and stresses in the tubes and tube sheet. Now let's see how to make a packed joint. Standard Navy stuffing boxes are packed with 4 rings, 2 rings of fiber, which swell in water to make a tight joint, and 2 rings of soft metal, caulked into the stuffing box threads to hold the fiber rings in place. Tools for a packing job are a loading pin, a caulking tool, and a wooden mallet. Use the loading pin to guide the packing rings into position. A fiber ring goes first. Use a caulking tool and with 1 or 2 light blows, caulk the ring to the bottom of the stuffing box. Next, a metal ring. Caulk with 3 or 4 light blows, just enough to fill the stuffing box threads with metal. Repeat these operations with another fiber ring and another metal ring. Always caulk rings one at a time, never as a group. For zinc maintenance, remove the zinc from its mount and chip off the scale, or machine it off. If more than half the zinc has been disintegrated, discard it and get a new one. When you replace the zinc, be sure there's good metal-to-metal contact with the zinc support. Repairs involving water tightness must be tested for leaks. The tests are the same as used for inspection: the flooding method, the compressed air, and soapy water method, or the water pressure method. This has been a general description of condenser maintenance. For operation and maintenance details of the tools shown in this film, refer to manufacturer's publications. For complete instructions covering condenser maintenance, refer to Bureau of Ships Manual, Chapter 46.